All right, folks, it's Bass Action, back in action here. In this video, we are going to go over how to find the area of a regular polygon. So if you've got a foldable, you can open up your foldable. We're going to be on the inside left and find the section for regular polygons. Now, in class, we'll spend a little bit more time developing where this formula comes from, but for starters, I'm just going to give you this area formula, and we're going to go through two examples. Now, the area formula for a regular polygon has a new vocabulary word in it. When we write the formula, it's written 1/2, and we're going to do a lowercase a and a capital P. The lowercase a is going to stand for a new segment called the apothem, okay? Some people call it the apothem, but I'll say apothem. The capital P is going to stand for the perimeter of the polygon that you're working with. All right, so 1/2 the apothem times the perimeter. Now, the two examples that I have here are important compare and contrasts. We're going to start with this hexagon, and a hexagon is a very, very important shape for us. On the hexagon, you're going to have a couple choices of how you can go about this, and we'll do enough of them that you'll probably have some of these numbers eventually memorized. On the regular hexagon, remember, from the front of this foldable, we can find the measure of one interior angle using our formula on that we did on the front, the 180 times n-2, and then divide by your number of sides. That would get us to an interior angle of 120 degrees. Now, the apothem is going to be, we're going to kind of eyeball where the center of our polygon would be, and an apothem is going to be a segment that's going to go from the center and is going to be perpendicular to a side. Now, the apothem is not only going to be perpendicular to the side, it's actually going to bisect that side, and in class we'll talk a little bit more about why that happens. So we're going to have our apothem, it's going to be perpendicular, it's going to bisect the side, and then we're going to also draw in a radius of the polygon. A radius of the polygon is also going to start at the center, and it's going to connect to one of the vertices. Now, when we draw in the radius of the polygon, it's going to bisect this angle. So if one angle inside this hexagon was 120 degrees and we draw in a radius, then this new tiny angle right here is going to be 60 degrees. Now, that's one way to get that. We could also get that angle by working up here on the central angle, and I'll show you how we're going to do that when we work on our pentagon over here to the right. But for right now, we've got our 120 degrees and we've got our 60 degrees down here. This tiny triangle right here is going to be key to working with our area formula. So you've got to always find that little tiny triangle before you do anything else. Now, let's go ahead and look at our formula. Our 1/2, our apothem times our perimeter. We can see that we're given a side of the regular polygon is 8. Okay, so we're given this 8, which means we know what the perimeter is going to be. We need to find this apothem. If one side of the polygon is 8 and it gets bisected by the apothem, then this little piece right here is going to be 4. We have a nice 30, 60, 90 triangle here, and this 4 is going to be half, or is going to be the short side, so it's half of the one side and it's the short side in the tiny triangle. So from the short to the apothem, and we can see the apothem in this case is across from the 60 degrees, so it's our long, so our apothem is going to be 4 radical 3. Now, if you've forgotten your 30, 60, 90 ratio, remember that's a 1 radical 3 and a 2. We're starting on the short, and we need to go to the long, so we just multiplied. Now we actually have the numbers that we need, so this area is going to be pretty easy. Our area is going to be 1/2. Our apothem, we just found it, was 4 radical 3, and the perimeter, there's 6 sides in the hexagon, and each side is 8, so our perimeter is 48. So if we just multiply this across, I like to do 1/2 times 4 is going to be 2, and then that 2 times the 48 will give me a 96. So the area of this is going to be 96 radical 3, and ours is centimeters, so we'll say centimeters squared. Now, All the hexagons will follow this same pattern. It will always have that nice 30, 60, 90 triangle in it. The pentagon, however, we're going to have to find a different angle measure. As I mentioned earlier, we're going to need the tiny triangle. So we're going to eyeball our center. We're going to draw in our apothem, make it perpendicular. Remember, it bisects. Again, we're starting with the side of 8, so we can put our 4 here. We're going to draw in the radius, and now we need to find some angle measures. We have a couple options of how to do that. One option is to use the formula again on the outside of this foldable to find the measure of one interior angle in a regular pentagon, and you would find that one interior angle is 108 degrees. So if that angle is 108 degrees and we draw in the radius, this small angle right here is going to be 54 degrees. Another option, and you just need to choose which one's going to work for your brain, another option is to imagine a triangle right here, okay? Inside this pentagon, there would be 5 of these triangles, okay? That would make 5 central angles. We know all the central angles would add to 360, so we could take our 360 divided by 5, and that would get us 72 degrees for each central angle. Then we would divide that 72 degrees by 2, and we would get this angle up top here as 36 degrees. It really doesn't matter which of these you find first, but you should find them both, because sometimes you'll want one and sometimes you'll want the other. Now, to find the apothem on this problem, what we need to recognize is this tiny triangle here is not a special right triangle. On the hexagon, it was a nice 30, 60, 90. This one's not. It's a 36 and a 54. So the only way that we could find the length of this apothem right here is to use trigonometry. So I'm going to put a little X on that apothem so that we can find that. And I'm going to choose my point of perspective, and I'm going to choose to stand down here at this 54 degrees. Remember, we're working with the tiny triangle here, okay? Now, from the 54 degrees, I want the opposite. I know the adjacent, so I'm going to use tangent, just basic SOHCAHTOA. So I'm going to say the tangent of 54 is going to be X over 4. That means that I can cross multiply this just like we did back in chapter 8. So my apothem of X is equal to 4 times the tangent of 54. Remember, we don't want to type that in our calculator and get the decimal right now. We want to keep this beautiful expression right here. To find the area, we're going to use that. We're going to say our area is going to be 1/2. We see that the apothem, we're going to use that what we just found, 4 times tangent 54. And then we're going to fill in the perimeter of our pentagon. So now we have a side of 8, but there are only 5 sides, so our perimeter is now only 40. Now, if you just type this in your calculator, 1/2 times 4, I would probably do 1/2 times 4 times 40, and then I would do the tangent 54. It makes the parentheses a little bit easier. What we'll find is that the area of this pentagon, regular pentagon, is going to be approximately 110.1 centimeters squared. Okay, so an important thing that you need to remember is that hexagons will always create a nice special right triangle on the tiny triangle. Our pentagons will not. We will always have to use trigonometry.